is a combination of rotation and translation. It follows that the kinetic energy of a rolling object is simply the sum of its blank, blank, blank and its blank, blank, blank.
Rotational kinetic energy and translational kinetic energy.
Right you are. It's the sum of the rotational kinetic energy and translational kinetic energy. In the space below, write the equation for the total kinetic energy of a rolling object. Okay? The general form, not the alternate form. The alternate form is really messed up. You'll never remember it. Okay? But the general form, the kinetic energy of a rolling object is the translational kinetic energy, 1/2 mv squared, plus the rotational kinetic energy, 1/2 I omega squared. Okay? Now, so if you had a ball on an incline, it has the center of mass has a velocity, and you have an angular velocity. Okay? So you have two types of kinetic energy. Here's what I want you to think about for a second. Think about one of those rolls of tape that I connect to a string and I swing around like this. And this thing's moving in a circle. And I ask you, hey, what's the energy of this thing as it moves in the circle? And I tell you that it's moving with a speed v and it has a mass m. So if I ask you what's the energy of this thing as it moves in a circle, what are you going to say?
1/2 mv squared.
1/2 mv squared, okay. But some people are sitting there looking at this like, yeah, but, what?
Different V at every point in the circle.
Well, the direction is a different V, but the magnitude is the same V, and the magnitude is what's in that formula. So that's really not an issue. But some people look at this and say, well, wait a minute, Mr. Cox. That's moving in a circle, right? I'm like, yep. If it's moving in a circle, it's like rotating, right? I'm like, yep. So why couldn't we think of this as a rotational kinetic energy? And I'm like, you could. If you chose to, you could say that thing has a rotational kinetic energy. And what would it look like? Well, Ke rotational is 1/2 I omega squared. And you certainly could talk about this thing going around in a circle in terms of some rotational speed. In fact, there's a pretty simple relationship between the translational speed and the rotational speed. What is it? V equals R omega. If we were talking about a roll of tape on the end of a piece of string, we'd probably treat that roll of tape as a what, Elliot? Piece of tape into a string, probably treat it as a, anybody?
Point mass?
Point mass. Anyone remember the moment of inertia of a point mass? mr squared. So I could come over here, I say, okay, I got my I, mr squared. My omega, if I do a little rearranging, is V over R, and both of them need to be squared since omega was squared. Boom, boom. 1/2 mv squared. Are you wrong if you choose to think about this thing moving in a circle as having a rotational kinetic energy? You're not wrong. Are you wrong if you choose to think about moving in a circle with a translational kinetic energy? You're not wrong. Well, it's the only way you can be wrong. If you add them. You can't say it has both. It's either got a translational kinetic energy or big or a rotational kinetic energy. It doesn't have both. This ball has both, but that piece of tape on the end of the string doesn't have both. It has either or. What's the difference? I hear for you too much.
Okay.
Okay, yeah, hammer.
Oh, the shape is different.
Nah, care less about shape. Fine, Arjuna.
The difference is in the ball, the center of axis of rotation is moving, and in the other one it's not. It's like the spinning wheel that you hold versus the spinning wheel that you spin and then walk with.
That's a good explanation. Over here, the axis is moving. The center of mass of the system moves through space. Over here, the average, if you will, location of the center of mass is the center of the circle over a period of time. And that average location for the center of mass doesn't move. That's why you got to say it's either or over here, whereas over here, this thing has both types. Okay?
With the whole translational equals rotational thing, doesn't that work only if it's a hoop, though? Because the
Only if it's a point mass or hoop. Yes. If you had some other shape, it wouldn't be exactly 1/2 mv squared.
Are we ever gonna come across a situation where the tape would be moving itself in the, like if it was like a loose string holding it and it?
Well, yeah, you could have, as one of my students said earlier today, it's like, Mr. Cox, how about if you were twirling the tape about, and as it twirled, you walked across the classroom? Well, that would be a situation where I would say the center of mass is moving, right? So I would have to consider the translational energy in addition to the rotational energy going around. Okay? So, number 3, in this expression right here, the I is the moment of inertia about the axis or center of the rolling object. Okay, we got 3 example problems. See if I can make it through them. I've been struggling with this, but we're going to try. Ooh. Okay, so our first one. A solid ball of radius r and mass m rolls at speed v across a level surface, which transitions into a 30-degree incline. So I got a situation that looks like that. We got a solid ball. Okay, and it's moving with a speed v, but it's rolling, so there's also an angular velocity.
Thank you.
And we want to know how high up the incline will this ball go before it runs out of gas, so to speak. Okay? Now, when you look at the picture I draw on the board, do you see one thing changing location?
Yes.
Yeah. If you see one thing changing location, that's a familiar situation for us, and we have an approach for that we like to use. What do we like to use? Conservation energy. The game hasn't changed. We've just added one more player to the game. Okay? We're still going to use conservation of energy. But when we look at the before picture, what type of energy do we see?
Translational as well as rotational.
We see translational, like always, 1/2 mv squared, but we also have rotational, 1/2 I omega squared. So that's my before energy. What happens to the energy? When this thing rolls over to here, what happens?
So is gravitational potential energy.
It's going to run out of gas. And when it gets up here and it stops moving, the only type of energy it has is gravitational potential energy, the formula for which is mgh. Okay? Very good. I for a solid ball, anyone remember? 2/5 mr squared. You don't have to have that memorized, guys. I is 2/5 mr squared. Omega squared. There's the linear velocity of the center of mass and the rotational velocity are linked as long as it rolls without slipping. And what's the link? What's the equation that relates the two?
V equals R omega.
V equals R omega. If it's not slipping, that's true. Okay? So I can replace omega squared with V squared over R squared. And if I look at what I have up here, we can start making some magic happen. Things you notice. R squared cancels. Righto. What else do you notice? Mass cancels. Here, here, here. Okay? And we write what we're left with. We have 1/2 V squared plus,
1/2, 2/5.
okay, that'd be 1/5 V squared, but I'm going to write it as 2/10. That's why math teachers always love me. Okay? Yep, that's 2/10 V squared. And that equals GH. The reason why I wrote it as 2/10 is I was looking ahead a little bit. Because my next step, I'm going to add 1/2 V squared with 2/10 V squared. Common denominator of those two fractions is 10. So you get 7/10 V squared equals GH. So, you can write this a bunch of different ways. But I'll write it like that. Okay? Now, so that's how high you go. And certainly, and of course, it depends on gravity. And depends on how fast you're initially moving. That both those dependencies make sense. Okay? Doesn't depend on the mass of the ball. Doesn't depend on the radius of the ball. B. If the hollow ball is replaced by a hollow spherical shell, okay, of equal mass and radius, what happens to the height? So in other words, I take this, I said, no longer solid, I'm going to concentrate all the mass just at the outer edge. Like a basketball, soccer ball, any type of normal athletic ball. Okay? So what happens to the height now? Well, first of all, what is moving from a solid ball to a hollow ball do? Changes the moment of inertia. For a hollow ball, anyone remember? Not 1/12, 2/3. Someone said it. Again, guys, I don't need you to remember the fraction. But what you should remember, if I go from solid to hollow, okay, the moment of inertia should be going up or down. it should be going up because the mass is getting moved further out. And 2/3 mr squared is greater than 2/5. Okay? I'm going to just go ahead and find the new height. Does this first equation change?
No.
When I change the shape? No, it's still translational kinetic energy plus rotational equaling GH. What does change is I.
The coefficient.
I can replace omega squared with v squared over r squared. That equals mgh. Masses, 1, 2, 3, cancel. R squareds cancel. 1/2 of 2/3 is? Dang it, you're still messing up. 2/6. Math teachers love me. Okay, 1/2 plus 2/6 is?
5/6.
5/6. Five, 6 v squared equals GH. So 5v squared over 6g equals h, and 5/6 is definitely a bigger fraction than 7/10. It goes higher. Okay? Now, do me a favor. Do in one sentence explain why it goes higher.
Because the moment.
Ah! Write it, everybody. You have 2 sentences if you need 2 sentences. Say, but I want everyone to write out in your own words why this thing goes higher. I'm going to call somebody. Okay. Someone I never hear from. Sarah.
I said it takes more effort to stop the law.
I agree with you. Can you expand on why it takes more effort to stop it?
Well, the mass distribution.
The mass distribution has changed, causing what to change? What has gotten bigger for that second hollow ball? The moment of inertia. So I agree with everything you said. It has gotten harder to stop the ball, but what you needed to continue to say was because the moment of inertia of the second ball is greater. Okay? So if that was a 2-point question, you probably would have got 1 or 2 points on the AP exam. You've got to give the reason. Okay? That's one explanation. I'll give you another. Okay? Here's another right here. If you build off that equation, it goes higher because the second ball has a bigger moment of inertia, therefore the total initial pool of energy is what? Greater.
Would it
Okay.
also mean that since they have the same velocity, there would have had to be a greater force applied at the beginning to get it to the same speed, so it has more energy in that case?
It's the long way around the bar, but you could say that, and it would take more force to get it up to that same speed. Yes. Okay. Moving on. Number 5. To make it around a loop of radius r without losing contact with the track, at what minimum height must a solid steel ball be released on the track? If the solid ball is replaced by a box that slides without friction, does the minimum release height increase, decrease, stay the same? Okay, well, it just so happens that I have a loopy-loop track back there, and we know, get it up guys, come on. Okay. So we've already, look, I'm getting a collection worksheet back here. Alright. You know, this is not anything new. We've already seen this before. Someone grab me a meter stick. Oh wait, I got one right here. Never mind. Okay, we've seen this before. This is nothing new. We know if I release it down here too low, the dude does a header back down, okay? And if I release it up here, it goes all the way around, okay? We've seen that. What I want to do today, though, is the problem we're getting ready to work asks us, there is a certain minimum height somewhere that you have to release this from for it to make a round. I want